Today we're talking about parent functions and transformations. This will be familiar to you. We did a lot of this last year, especially when we talked about parabolas. For each of these graphs, you should have a handout of this paper I want you to fill out and bring to class with you tomorrow. And for each graph, you need to discuss or include, write down the domain, the range, the end behavior, whether or not the function is even or odd, continuity, whether it's continuous or if it has points of discontinuity, if it's increasing or decreasing on what intervals, and any intercepts, x and y intercepts. And I know that's a lot of information. I'm going to show you what I mean when we get to the parabola. The first type of function I want to remind you about is a constant function. So an example, and I'd have to do an example on here to graph one, would be f of x equals 3. So then if we, let's assume, I'm just going to assume on all of these graphs that it's scaled by 1. So remember that when we have a constant function, it's a horizontal line. That's not writing very well. So we have horizontal line that passes through 3. That is our constant function. The next one is the identity function, and this is f of x equals x. And you might be more familiar with me saying y equals x, which means whatever value x is, y is the same thing. So if x is 1, y is 1. If x is 2, y is 2. If x is 3, y is 3. If x is 1.5, y is 1.5. And it would be true for negative values as well. So we end up getting this graph. I guess I should use my line tool instead, because that should be a line. So we end up with a line that actually splits the first quadrant and third quadrant, and that is the identity function. Quadratic function, of course, is parabola. And remember the points we remembered, it passed through 0, 0. And when we go over 1, up 1, over 2, up 4, that's because you square 1 and you square a 2 to get those values. And we to the left 1, up 1, to the left 2, up 4. So those were the moves we kind of remembered for a parabola. So I'm going to draw that in. So on this problem, I'm actually going to go through what I want you to show for domain, range, all that information. So on this problem, the domain is all real numbers. And remember, you can look at the arrows left to right. Domain is about x. The range, if you look at your graph, start at the bottom and move up, you can see that all of our y values are greater than or equal to 0. So we can say greater than or equal to 0. I'm going to write it this way. Oh, let's see. I need a bracket on this side. We want to include 0, and we want to go to infinity. So this is interval notation that we can use. I could have used interval notation here, negative infinity to infinity. So that's the domain and range. End behavior, remember with end behavior we can use limits. So I can have the limit as x goes to infinity of f of x. So when x goes to infinity, if x gets really large, f of x gets really large. So it's going to infinity. The limit as x approaches negative infinity of f of x. When x gets really small, f of x gets really large. So also it's infinity. And if you don't use the limit symbol and you just say as x gets larger, f of x gets larger, that's okay with me. Even or odd. This function is even. We can tell that because it is symmetrical to the y-axis. And remember we had a way to show this as well, and I'm not going to take the time to show it right now, but remember to show an even function, if we would substitute in f of negative x and show that we get f of x. And that's how you can show it's an even function. But it is symmetrical to the y-axis, so we know that it's even. Continuity, this is a continuous function. There's no, remember our easy way to do that was that to look for, or to check whether or not you can draw the function without lifting your pencil, and we can. So this is a continuous function. So I'm going to write down continuous everywhere. Increasing and decreasing. Well, we can see that it is, again, from left to right. When you first start off going left to right, you're falling first, so it's decreasing, and then you're increasing. So we could say it's decreasing from negative infinity to the vertex, which is 0. Remember, it's about the x values. When you talk about the interval where it's decreasing or increasing, you're reporting the x values. And it's increasing from 0 to infinity. And one thing I didn't add up here, but I think I might like to, is extrema. So if you have any extrema, remember the mins and maxes, let's include those as well. So we have an absolute max, absolute min at 0, 0. And remember, we talked about how if it goes from decreasing to increasing, that means it had to have gone through a minimum at that point. And the last thing would be the intercepts. The x-intercept is 0, and the y-intercept is 0, where it crosses the x-axis, where it crosses the y-axis. So that's a lot of information I'm asking you to include. You might be able to do it more organized than that. And but I'm going to go on to the next function. I'm going to leave the rest of the information for you to do, but we'll just talk about the parent graphs. For cubic function, and you should be able to picture what that looks like, passes through 0, 0. If you cube a 1, you get 1, and if you cube a 2, you get 8. And if you cube a negative 1, you get negative 1. If you cube a negative 2, you get negative 8. So we end up with this function. All right? And you'll be able to go ahead and add all that other information, please. Next one's the square root function. Remember, that looks like a parabola on its side. Passes through 0, 0. The square root of 1 is 1. The next smart value to plug in here, we want it to work out evenly or accurately. So the square root of 4 is 2. So I would mark that. So I get this shape. And again, this is a review. We've done these before. And so go ahead and, again, write down all the other information for that. The reciprocal function, and it's also a rational function. This one, I'm going to plug in some values. First of all, notice that x cannot be equal to 0 because we get an undefined value. But if x is 1, 1 over 1 is 1. If x is 2, 1 over 2 is a half. If x is a half, 1 over a half, you'd flip that over and you'd get 2. And so we end up getting a graph that looks like this. And it actually gets closer and closer to the x-axis going this direction, gets closer to the y-axis as it approaches 0. And in the negative direction, we end up with kind of a mirror here. So if we plug in a half, we'll get negative 2. If we plug in a negative 2, we'll get negative a half. So with those, notice it doesn't take very many points. Oops, that didn't go too well. To get an accurate sketch of the graph. Again, now this time, notice I had to lift my pencil to draw that one, so it's not continuous, so you'll need to name the points of discontinuity on that one, or the types of discontinuity as well. Absolute value is another familiar function to us. Absolute value of 0 is 0. Absolute value of 1 is 1. Of 2 is 2. Of negative 1 is 1. Of negative 2 is 2. So we end up with a V-shaped graph. And notice that this actually, if it hadn't been for this part here on the negative side, it would have looked like the identity function, f of x equals x, that we just got done discussing. But because we're doing absolute value, everything that was below the x-axis got reflected up above, so we end up with a V shape. This next one is a little newer for us. I don't think that we did this last year, and it's called the greatest integer value function. Kind of has a weird notation, looks like little double brackets. All it means is, for example, if I wanted to know, if I had the little symbol with double brackets of 3.5, I'm asking for the greatest integer that is less than or equal to 3.5. And the answer would be, the largest integer that's less than or equal to this would be 3. And to kind of explore what the graph looks like, we're going to use our calculator. Actually, let me show you on the calculator. You can evaluate these. If you go math, number, and you want number 5, where it has int. And if I type in a 3.5, I get 3. If I do the same thing and I type in, let's try a 3.9, I get 3. Now if I were to do this and type in, say, a 4.1, I get 4. So I'm going to take a look. I'm going to type into this the function. So I'm going to go math, number, and I'm going to choose number 5. And I want to put an x here. So it's going to plug in values for me. And before I look at the graph, I'm going to set up a table. Let's start the table at 3 and go in increments of 0.1 if you want to go ahead and try this. Set it to auto and auto because it's going to fill in values for me. Now if I look at my table, notice what's happening. I have, if it's 2 point something, it's always going to go down to 2. And when I get to 3, it jumps up to 3. And it stays at 3. It stays at a height of 3 until I get to 4. And then it's going to jump up to a height of 4. So when you look at the graph, it's going to do, well, if I typed in a 0, it would stay at 0 until it got to the 1. And then it would jump up to the 1. And then it would jump up to the 2, and then jump up to the 3. And now the open circles, and they're going to be hard for me to draw on here, are going to be on this end because I had that backwards. These are going to be the closed in ones, and the open circles are going to be on the ends here because it jumps up at that point. So it kind of is hard to draw those on there. If we look at our graph, I'm going to go zoom 6, and you'll see it will draw those on there. Now, this is sometimes, and you'll know why, this is sometimes called a step function. And you can see why, because they kind of look like stair steps. All right, so that is a greatest integer value function or a step function. Vertical and horizontal translations, you should be very familiar with this, especially with a parabola. This shifts the graph without changing the shape. So my question I want you to think about, how does f of x equal x plus 1 quantity squared minus 3 compared to the parent function f of x equals x squared? So pause the video and think about it for a minute. Now you should have remembered from Algebra 2 that the plus 1 inside the parentheses is going to shift this 1 unit to the left, and the minus 3 is going to shift this 3 units down. Here's a problem that's a little different. We've seen how this x plus 2 quantity squared would shift it 2 units to the left, but what if the function's in standard form? So I want you to try this. F of x equals x squared plus 3x plus 1, and we're going to compare that to what I've called g of x equals x plus 2 quantity squared plus 3 times x plus 2 plus 1. So I want you to make a prediction, kind of pause the video, make a prediction, try it on your calculator after you make your prediction and think about what you think might happen. So were you right? Notice on mine I have the transformed one in a thicker line on my calculator, but even in that format it shifted it 2 units to the left, and that's because I added 2 to both of the x's. If I had only done it to one of the x's, well, you can check it out and see if you would get a different result, but pretty sure you will. On this one, we're going to use the parent function f of x equals x cubed to graph g of x equals x minus 2 quantity cubed minus 1. So think about what's going to change. Remember what this does. 2 to the right this time goes the opposite direction of the sign, and this one down 1. So our point of inflection is going to move. Instead of 0, 0, it will be at the point 2, negative 1. So I'm going to plot that point to start with. Now I'm going to use my parent graph. Remember, it was from my point of inflection, from my locator point. It was over 1, up 1, and it was over 2, up 8. And then from that point going the other direction, over 1, down 1, over 2, down 8. And then you can draw in your graph. Now notice compared to my parent graph, think about things like, did my domain change? Did my range change? Did my end behavior change? Is it still continuous? So if you go through all those things on your parent graph function sheet that I had you guys fill out, make some of those comparisons and see what you think changed and what didn't. Again, here's another one you're familiar with. F of x equals the absolute value of x as our parent graph, and we're going to graph x plus 1, the absolute value of x plus 1 minus 3. So again, this is going to go to the left 1 and down 3, so I'm going to mark my locator point. And from there, now out in front here, if there were a number here, this is the number that acts like the slope, or that would be like our vertical stretching or compression, and if there's nothing there, it's just a 1. So then it's going to be just like the parent graph. So we're going to end up with a V shape opening up because it's positive. And we draw this in. And there's our graph. We have talked a lot about reflections in the x-axis, how if you put a negative in front of your formula, if you do negative f of x, it reflects it over the x-axis. If you put the negative inside the function, then that's going to reflect it over the y-axis, which also, if it reflects over the y-axis, remember that was a way to tell if it was an even function. So on here I'm going to write a function to reflect this in the y-axis. So I'm doing just like I would if it was an even function. I would change it. I'm going to evaluate f of negative x. So I get 2 times negative x quantity squared plus 3 times negative x minus 1. Squaring a negative is still going to result in a positive. This would be minus 3x minus 1. So take a look, take a minute to type this into your calculator and then this one, and compare those. You're going to see a reflection in the y-axis. So here's my 2 graphs, and if I do zoom 6 with a standard viewing window, I'll see the first one, and now I see the second one, and notice how if you rotated this around the y-axis, this piece would get reflected onto this outer piece here. So you can see that it is a reflection across the y-axis. And notice, even though I make that comment that it is a reflection, you can see the reflection in the y-axis, this is not an even function, because to be an even function, f of negative x has to equal f of x. And clearly it doesn't, so it's not an even function. The last thing I just want to mention, and this is in your book, although I've written some things on it, what they call vertical dilations. And we use these when you have a number out front of your function. We talked about how it's stretched or compressed last year in Algebra 2. So if the number was bigger than 1, it would be stretched, it'd be skinnier. If it was a fraction, something between 0 and 1, then it was going to be wider and compressed. What we didn't do, we didn't talk about horizontal dilations, which means you take the number inside the parentheses or inside with the x value. And what happens there is it's compressed if the value of a is bigger than 1 and you're putting it inside the function with the x. And then it's like you're pushing it together, so it's compressed together. Or it would be considered expanded horizontally. Imagine that you pulled these two things apart. And that's going to happen if you have a value between 0 and 1 that you're putting into the function as a coefficient of the x.